Good afternoon. It's a pleasure to welcome you, a small group of people from around the world. I can see some names from different places. My name is Marek Michalewicz. I'm the director of Interdisciplinary Center for Mathematical and Computational Modeling, University of Warsaw. In short, ICM. ICM is the organizer of this series of seminars in computer and computational science. It grew in a sort of ad hoc and the natural way as a continuation of our Supercomputing Frontiers Europe 2020 conference. And today we have a great pleasure of welcoming Michael Bussmann from CASUS, Center for Advanced Systems Understanding, Helmholtz-Zentrum. This new CASUS Center is being established, and most probably Michael will tell you himself about what it is. But just to share a little bit of personal reminiscences about this, I had a great pleasure of being invited for the very first inaugural workshop organized by CASUS. CASUS is located in a very, very special and beautiful little town on the border of Germany and Poland called Görlitz. Görlitz is an extraordinary place. If you ever travel through Central Europe, please visit Görlitz. It's extraordinary in the sense that it hasn't suffered during the Second World War. And there are beautiful buildings going back to 13th century, 15th century. There are several hundred of historical buildings listed as a heritage places in the UNESCO list. So it's beautiful. On one side of Nissan River is Görlitz, on the other side is Zgorzelec. Interestingly enough, both of my sisters were born in Zgorzelec, so my family goes a long way there. They moved there right after the war. My mother and my father, they met there, so that's a place very close to my heart, although I wasn't born there. So we have a guest from that very special city. And I met Michael over 5 years ago. Michael was the first, one of the speakers in the very first conference, Supercomputing Frontiers, in Singapore, 2015. So it's a great pleasure to have Michael and to speak today. But I'll leave it at that, talking about today's seminar. Right now, I would like to whet your appetite and introduce topics of the next 2 seminars, and I would really like you to sort of keep coming back to our seminars, because each one is different. Each one would feature the very, very different topic and a speaker. And here, the next one on May 7th, we'll have the great pleasure of hosting Simon Match from Melbourne, Australia, from the University of Melbourne. Again, Simon is an astrophysicist, but he is also involved in a new organization, which is called Melbourne Data Analytics Platform and Petascale Campus Initiative. And the University of Melbourne is one of 2. I have to say 2 because the other one is the one that I graduated. It's the Australian National University. But both of those universities are sort of the leading research universities in Australia and the Southern Hemisphere. And lots of very interesting things, very creative, are going on there. So I encourage all of you, and please spread the word, tell your friends, especially from the circles of astrophysicists, physicists, cosmologists, modelers, HPC experts, data science people. And let me now introduce a speaker who will be talking on the 14th I have a slide, please. We'll continue with the topic of quantum computing. And this time, we'll have the honor of having Professor Catherine Margouch speak about what do we know about performance of quantum annealing systems. Catherine has been a professor of computer science at Amherst College for 30 years. Her specialization interests lay in the algorithms, computational complexity, and complete problems. And for many years now, quantum annealers and quantum computing. And since 2014, Catherine moved to work in D-Wave systems. And of course, there's lots of controversy. She herself created a big controversy when she first presented the special way of benchmarking quantum annealer. And that, of course, met with lots of polemic and people who are in the so-called gate quantum computer world. Most of them are actually. Quantum annealer is a much smaller camp. Sort of were very critical. Well, let's see what Catherine has to say about this and other things. So I presume that will be very fascinating. Now let me acknowledge our partners, especially media partners. That's HPC Wire, Tabor Communications, Datalami, Enterprise AI. And with that, I welcome you to the talk by Professor Michael Bussmann. Thank you.
Thank you very much for coming over, all of you. Thank you very much, Marek, for inviting me. It's a pleasure to take part in this seminar series, and I really like always to come back to supercomputing frontiers, and I really like this series you have set up by now, and I really appreciate being part of it. And I will surely watch the next ones coming. So this is great, and I'm happy to take part in this one. So without further ado, I will try to now share my screen. Let me just quickly check again. There we are. And start our talk that I'm going to be showing you on today. See, there we are. So today I'm going to talk about some of the stuff that we have been doing at CASUS, not all of it. CASUS is actually a new center, as Marek already told you. That is actually a center that joins together several partners. First of all, my institution, Helmholtz-Zentrum Dresden-Rossendorf, which is one of Europe's national labs. On the other side, there is another national lab called Helmholtz Center for Environmental Science, UFZ in Leipzig, a Max Planck Center, a Max Planck Institute for Cell Biology in Dresden, a Polish University of Wrocław. So we are really a German and Polish institution. And on the other side, we also have the Technical University, and both universities in their countries are excellence universities. So what we really have is very strong partners bringing together what we want to set up here in Görlitz as the Center for Advanced Systems Understanding, where we fuse HPC and data science to really understand in a modern way, complex systems. So if you have been looking at any news, you know that tackling a challenge, for example, like COVID-19, is something that you need to do interdisciplinary, where you need to do modeling, where you need to do data analysis, and you cannot do it in a single way just with epidemiology. You have to understand other parts. You have to understand social parts. You have to understand economic parts, and these all have to fit together. I'm not going to talk about our efforts there today, also because I want to take off your mind for some hours of this subject, but I also want to show you what has actually become possible with what I would call discovery machines. And discovery machines in the strict sense is the way I'm going to talk about is going to be your standard HPC system in some sense, and how to use it in the future. But this will actually just be part of a discovery machine, and I'm going to show you why and how. So where we are going to start with is actually big science. And big science you see here, big science means that wherever we go now in terms of science and in terms of doing science at different facilities, the most interesting and forefront research is really done at large-scale facilities. Let it be CERN, let it be the European XFEL, the European Extreme Light Infrastructure, the astroparticle parts like CTA or other parts actually. And the common thing really is here that what these facilities look at are really complex systems in itself. There is no fundamental theory anymore that really just predicts what is happening. For example, in particle physics, the standard model is given, but we're really now looking at new physics with much higher luminosity and much higher rate than we ever have seen before. And we will have very complex events to look at. And the same thing, biological systems, material systems, looking at them at the atomic scale is going to really happen at the European XFEL, making molecular movies there. Or at the Extreme Light Initiative, there will going to be the look at matter under really extreme conditions. So high fields, high power, high pressure, high temperature, and so on. And what we know there is that just the system itself is a very complex thing. But now we get data at a rate and quality that we never had before. And now we really have to fuse our understanding, what we know from first principles and what we know from experiments, to really form a concise picture of what we're talking about. So, it's taking some time here. There we are. And this is basically what I'm going to talk about. So we're not the only ones knowing that this will become a problem. DOE says it's way too much data for regular old computers. I find this a bit of a showy headline there, but nevertheless, partially it's true, and I'm going to show you why. So what you should keep in mind that the standard scientific process still exists, but it's going to be digital in the future, and it's going to be HPC and data intensive dependent. So where we are really going now is how to understand how to fuse these things and how to really make the scientific process a digital process in its complexity and completeness. So let's do data-driven science. We start, as always, with a problem, and the problem here is tumor therapy. So if you have a cancer tumor in a patient, you can actually do surgery, you can do something with chemicals and so on, so with drugs, or you can really do radiation therapy. So that's one way to treat cancer. And if you do it, you usually do it with X-ray beams, and X-ray beams only do not just harm the tumor, which you here see in the head of a patient in the center of the brain, marked in red and with that white line, but actually it also harms the surrounding tissue. And that's not a good thing, because you just want to kill the tumor and not the surrounding brain or the eyes or anything. If you do not use X-rays, but really particle beams, ion beams, so the center of our atoms, the nuclei of our atoms as beams of particles to kill the tumor, you can precisely direct the dose, the lethal dose that kills the tumor in the region of the tumor. And this is great. The problem with that is that you need large-scale facilities with that. I hope you can see this on your screen. If you look at the very bottom of this, and I'll try to use the cursor, and I hope this works. So if you look here at the bottom of this picture here, that's the patient, and that's 600 tons of steel rotating around the patient to actually deliver the dose. That's a huge facility. That's a costly facility. And what we have tried to do in the past few years is to actually replace this with a high-power laser system and a very small guidance system of a few meters that would actually replace this big system and use it for radiation therapy, making it widely available to patients and so on. The problem with this is the technique itself. So what we really just want to do is we need a target. You can think of it as a standard metal foil and ionize the matter inside the view of the high power laser to a full extent. So meaning that the high power laser really rips the electrons from the atoms and pushes them forward. And then the ions, the inner core of the atoms, follow those electrons and by this get accelerated. And this is a highly violent, nonlinear process. Okay, your audio has started to sound weird. I hope I changed nothing, so I hope this is still going and it's not my connection. I hope you can still hear me. So if we're doing this, we first need to understand it from first principle. And what we basically did was setting up standard HPC simulations for this from the atomic resolution up. So really going from the single electron, from the single ion, and simulating a full piece of matter and taking every electron and every ion. And this is extremely important. This is a huge scale HPC simulation. And we already did the first one in 2015 with a very nice and interesting setup where we just took a very, very tiny target, a levitating sphere. We actually let it levitate and fire at it with a laser. So this little target was our source for the ion beam. And this was especially a very nice experiment because we could model it at that time in its full extent so that we really could do a simulation that in principle could take into account all the effects we were seeing in the experiment. And we did this blindly. So we did not know we did know the experimental conditions beforehand, but we did not know the results, basically because we got the HPC allocation before the final results of the experiment came out and were analyzed. And we did 2D and 3D simulations, and it became pretty clear right from the beginning that the 2D simulations wouldn't suffice. So we really needed to do a full 3D simulation. And actually going blindly there, we got, given that there are a lot and an enormity of nonlinear processes, this was an awesome hit, both from the qualitative but also the quantitative agreement between simulation and experiment. And to give you an idea, that was on the #1 system at that time, that was Titan, and we only had 7 simulations running on the full-scale system, 18,000 GPUs at that time, having 60 million CPU hours. And the data you saw here, this is about a few kilobytes of data max. And this is what we actually initially gathered was 4 petabytes of data that we had to analyze to really understand the physics of what was happening. And we still have a few petabytes of these at our own institution because we transferred them home. Don't ask me why, and don't ask me how, but we did it. And so we still have this data available, and we needed this high quality data to really understand the physics behind it, because in experiment at this time, we could not measure what was actually happening. So we fully had to rely on the simulations. Of course, you don't stop there. And now you take into account new effects that you see when you go to higher powers. You actually see that the influence of the time before the laser hits the target will become important. So the laser is not just a very short pulse of light in time, but it actually starts up earlier. And if you take this into account, you now have to do 6 orders of magnitude in time. And we did this, of course, and we did simulations. And 3 years later, we again asked for time, for computational time, this time on the #3 system in the world, Pittsburgh, asking for 109 million CPU hours again. And they wrote principle, this is a great proposal, but please reduce the data requirements and try to find a solution that is technically possible for CSCS. So for the number 3 system at that time, it was not technically possible to accommodate our data requirements. And they hadn't changed much. It was about 7 petabytes. You know, it wasn't that much. It's a few petabytes. We can deal with that. We know how to do that. And this goes on. And the reason for this is, of course, and many of you will know this if you come from an HPC background, is simple the hierarchy of bandwidth. So you can now churn in a lot of data with a single GPU, going there basically to a terabyte per second data rate in a GPU. But if you go down to the I/O level, if you even go down to the normal memory in your host system where the GPU is in, this is already much less. And if you really go to I/O, this is even less. So you can't actually store much of what you're computing anymore. But given a complex system where really scale effects play a role and where you need to know the microphysics in detail, this really becomes a problem. So some might say, oh, you just reduce and compress that data. But the problem here is that actually, if you compress the data, the compression you get strongly depends on the information in that data. So if you have high quality data with a lot of information in there, you won't be able to compress it that much. And if you really want to compress it to the max, you will need a lot of computational power. So this will mean in the end that actually storing and chunking the data the way you want it will actually take longer. You might reduce the data by some amount, but really your bandwidth, your actually bandwidth that you're living with, your I/O bandwidth won't go up because you're now storing reduced data, but you actually have to wait longer. So your throughput of your data will actually go much below what you saw before. And this is a critical issue to understand. So what you really have to do is throw data away, but you have to throw it away intelligently. Okay, and so simulations of complex systems, to give you an overview, no longer create predetermined data sets of interest. So I can't just say I want to have that data or that data. I really have to look into which data is really interesting for me. And those simulations now produce amounts of data that can no longer be written to file and that cannot be transferred elsewhere, but that have a limited lifetime on the systems we're working at. And this is critical because you're basically running a simulation, and after a year, you have to delete that data. But a PhD thesis is 3 years, and you might not have finished with analyzing the data. And you can't even get the data from that system anymore via the internet or anything. So this is a critical issue in how we have to change our workflows here. Okay, if you really want to learn something in physics, you have to do experiments. So not just simulations, you have to do experiments. And our institute paid a lot of money, several 10 million euros, to actually do these experiments on the same scale that we do the simulations. And here's the reason why. If we go to higher intensities and thus higher energies for our particle beams, the laser gets higher intensity and the final particle beam gets a higher energy, and with a higher particle energy, we can actually penetrate the tissue deeper and get deeper seated tumors to be irradiated. So this is very important to catch a lot of tumors in the body. But then the beams start to behave weirdly, the particle beams. They filament. So you really see this, that things are happening there on a very small scale that we need to understand, because where you see now higher color or lower color, higher intensity and lower intensity in these pictures here, actually it means that you have more or less particles. And this means more or less dose. And this means the ones where you see lighter color, this is actually more deadly to the virus than these parts that might not harm the virus at all. Not the virus, see COVID-19, the cancer. So sorry for that. So the actual idea here is to understand what's happening here and to control this here, both via simulations and experiments. And for that, we created HiBEF, the Helmholtz International Beamline for Extreme Fields. So this is the basic setup. This is happening at the European XFEL, a large X-ray laser about 3 kilometers situated in Hamburg in Germany, which costs in total about 1.5 billion and is really a camera that can do molecular movies, that can do movies on the atomic scale. And we want to analyze those movies and compare them to our simulations on the fundamental scale that we know. But if we do that, we actually find out that the pictures that we get out are not the ones where we really want to know. We get out scattering pictures, which are basically an FFT squared of what we actually want to see. And if you ever have known FFTs and have worked with FFTs, an FFT squared is actually something where you lose information. You cannot simply invert the square of an FFT again with the inverse FFT and get the original picture that you want to look at. So this is really important. Above you see different side views of a foil that we hit with a laser coming from the left, same here. And depending on the physics, we get very different scattering pictures. So this is amazing. So we can really see the different physics happening that are important to us in the different pictures. However, what we can't really do is go from the lower picture to the upper picture. And I'll come back to that. But if we really do these experiments, again, we get petabytes per hour. We get all this high-resolution scattering data, this high-resolution imaging data at megahertz or kilohertz rates. And these are enormous pictures. Each of them has to finally give us atomic resolution there. So again, we have petabytes per hour data rate coming in. The same with the simulations. So you will say, petabyte. Big data analytics is so old school, but the problem with big data analytics as it's been done usually is you have easy data and automated processes to look at. Yeah, I know AI, image reconstruction, this is all complicated and things have been done, but there are things that are not easy to do in AI. And this is for especially for nonlinear problems, and this is especially for non-convex problems. So AI might be very good for that, but you have to find trustful algorithms that actually do this at a megahertz rate with petabyte data coming in per hour. So this is really important. And usually the standard algorithms for these are iterative algorithms. So I don't know when they will really converge in what time. And this is critical if you have a data deluge coming at you. You need to know for sure when your work on that data is done. So iterative methods are bad by themselves, and they can't really give you a good information. Here you see a picture of a dog and a cat. And if you take that part out of that picture, if you do a scattering actually on that picture, and if you take out the part of the picture that you lose in our measurements and replace it, actually exchange that part that you would get for a cat and put it back into the dog picture, and take the part of the dog picture that you're missing and put it in the cat picture, you actually see that what you would get out looks much more like a cat, although it's a dog, and it looks much more like a dog, although it's a cat. So this is really important. So we're missing critical information that is not in the fundamental data, and this is still a very big problem. So we are really dealing with incomplete data here and non-global optimization of stuff. So, of course, one of the things that you can do is basically do a full forward analysis and really do a scan through all the relevant parameters and see whether your simulation matches your experiment. But this means you do not just simulate the system anymore, as I just showed you in this standard HPC task. You now also simulate the facility, the full European X-ray FEL, the full free electron laser, the full X-ray laser, needs to be simulated in order to really understand how the radiation interacts with the system you're looking at. And on the other hand, you have to simulate the detectors. You have to simulate really how this data is taken and how it is detected, because this again gives you some more information on what you're actually seeing. So you need to do a full synthetic experiment. And remember that just this tiny part is already a full-scale HPC simulation. So this is a problem. And this is what CERN has been doing for 30 years, by the way. That's exactly why CERN became so successful, because they just did this, but they did it for a single purpose. And at these facilities that I'm talking about now, we're just one customer of 2,000, and everybody, each of these 2,000 customers comes with their own specific problem, with their own specific physics. And this is a real issue. So we're not alone with that. And the fundamental problem here is not volume or rate. We can deal with volume or rate if we know what we're doing. But if we are looking at a complex system that we don't really know in the beginning when we start the experiment, this is the problem, because now automation is an issue. The other thing that has really changed is because the data has become complex. In the past, we could very easily and with highly intelligent algorithms throw everything away that we haven't been interested in. Now we can't do this anymore. So this meant that we reduce the data by orders of magnitude in the beginning and then have it of manageable size for a much longer time. Now, this step happens much later, because only when the PhD student that has to deal with that really understands what she or he is doing, can we do a knowledge extraction and say, this is interesting, and the rest, 99.999% of the data we can get rid of. And this is a lucky situation. It might not be that the reduction is so strong. So this is really an issue. And this also means that if the data becomes complex, the computing effort to really extract the knowledge, to really understand it, becomes huge. You know this from AI, but also other data analytics algorithms, that as soon as the data becomes more complex, you have to do much more complex things on that data, and actually thus the computing effort starts to be growing in the same way as the data is reduced almost totally. And now the point is, you might think that an HPC system is an expensive thing, but such a facility is so much more expensive. Those facilities are usually 10 times or more oversubscribed, meaning they're, for each scientist doing an experiment, there 10 or 20 or 30 are angry that they didn't get through. And you only have 6 months of preparation to really do your experiment there, and you have to do it in 1 week, and it costs over 100,000 euros usually to do such an experiment, and you have one time in your whole PhD to do such an experiment. So the data you get there is really valuable in all kinds of senses. And if you've ever done a PhD, you know how nervous you would be that you only have 1 week in your 3 or 4 years of PhD to do things right. I've been there, I've done that. It's not a nice thing to have. And the problem is, if you can't analyze the data in that time, you're doing your experiments blindly. And that's what's currently being done often, because the data is too much to analyze on site right now. So we face 4 challenges. High data quality is a challenge. Complexity is a challenge, because we cannot seriously reduce it. The data rates themselves are a huge challenge. Petabytes of data in a few hours coming in. Short data lifetime gives PhD students stress, and their supervisors as well, I can tell you. But in the end, poor understanding of the complex system is where we are really at the core of it, because as long as we don't understand what we're measuring, and this is happening in science, that's what science is about, the 3 points before that really give us a huge ton of problems. So do we have ideas how to do this? Of course, that's why you invited me. But these are only partial ideas, and bringing them all together and finally forming a coherent picture, I think this doesn't exist yet, and this is a problem. But we're starting our path how to go there. And I think there are some crucial steps. So one of the steps is that we don't know which computing hardware. Still, we don't know. After 15 years of GPU computing and stuff like that, and FPGAs, we still don't know which hardware is best for which problem. And I think specific hardware might sometimes be best for a specific problem. But we don't want to really write software for all the pieces of hardware out there. We need to understand much better data dependencies and data flows and integrate them into our software, because almost no algorithms, of course, again, except for AI, really are compute bound anymore. Most of them are throughput bound, bandwidth limited. So this is really an issue. We have to better understand how communication and communication topologies can be abstracted to better fit codes on machines and have complex problems that evolve in a very dynamic manner, how to best put them on machines. We have to thus think in a better way of domain decomposition on such machines. We have to do a lot of in-memory. We can't store stuff anymore. So everything has to be done live. So we have to have feedback. We really have to work with the code, with the data analysis, with the simulation, with everything that's happening at the same time in a way that a human can still understand it. And think of it, if you're having megahertz rates, so a million images per second, how do you bring them to a human? I can't see a million images. We see movie. Maybe a gamer can see the difference between 30 frames per second and 60 frames per second, but not the difference to a million frames per second anymore. And finally, we really have to bring all this data together in one point to that one poor PhD student that has to understand it. So let's start with performant code. Performant code means it runs everywhere, and I want to write it once. So I don't want to do what you see there. I don't want to say if def CUDA do this, if def OpenMP do this, if def running in a serial sequential way do this. And what we have created is Alpaca, which is basically a library that allows you to exactly get rid of that. That it looks very similar in its elements. You see this here as CUDA. So you have a grid, you have a block, you have a thread, and you have an element level. The last one basically being your vectorization level. And you describe the parallelism in your code following this hierarchy of parallel levels. And actually these levels can then be mapped to different hardware structures and efficiently being mapped to those. And in the background, we use CUDA, we use HIP, we use OpenMP, we use SIGL, we use TBP as backends to fully exploit the hardware capabilities and to optimize for that hardware. But you just write one single C++ code that can run on a CPU, on a GPU, and on an FPGA. So this is something that we've been developing in the last few years, and we have been teaming up with our partners from VC, the library for vectorization, because vectorization is a special issue in this kind of thing, and we're really pushing now this software stack to not just HPC, where it's currently being used in the DOE Exascale program, but also for data analysis at CERN, at European XFEL, and other places, really. So this is important. And it works. It does not reduce your native performance, so it's on par with native performance. So here you see a direct comparison. It actually really produces the same bytecode. So basically, all the abstractions are thus just gone away by the compiler, and you get the boilerplate code that sometimes even is a bit better than what you would write by hand. And if you already have something that is working, for example, on CUDA, and you might know this if you have ever done HIP, if you use our library, Alpaca, you can basically use Kapla. I hope we have some Trekkies in the audience here, which is basically just a library that helps you to bring your CUDA code to Alpaca code. So if you have a working CUDA code, you just do a few text changes in your source code, and you are now running your GPU code on a CPU or an FPGA. So this is a cool thing. If you have some CUDA code lying around, you can try this out, and you just need Kapla to actually do what you want to do there. But this is just task scheduling. You also need to better understand how memory is actually used. So depending on if you're running on a GPU or if you're doing a vectorization on a CPU, you have to change your memory. You really have to change your memory layout. But your fundamental data structure should be the same, because you have created that data structure with a certain physical representation in mind. It might be a 3D vector describing an electric field, or it might be a scalar that tells you something on the temperature or something like that, or it might be an array of structs or something like that. But memory-wise, you might really want to change that representation depending on the algorithm and the hardware you're using. And again, we have been teaming up with certain people here with the root data analysis framework and present you Llama, low-level abstraction of memory access. This is an ongoing project. This has just started, where we will provide exactly this. You take your data structure as is, you really want to use it, but the memory layout is optimized for your hardware platform and so on. And this is going to be an exciting project. Have a look at it in the future. This is going to be huge. And it's interoperable with Alpaca. And you see llamas, alpacas, camels, you know, all the families there. Of course, this also must be shared with memory allocation and optimized deep copies. They will also be part of this endeavor. And we already have a working prototype for optimized object-like memory allocation on different hardware. So, for example, you can now do fast, small object allocations on GPUs with our malloc MC, which will be part of the Llama suite later on. Handling data flow is the other thing. You usually do, if you do task-based programming, so not just data parallel programming in a vectorized or GPU manner, but really also different tasks that can run in parallel, you would set up a task graph. But this is really complicated for large-scale projects where you really have to say, now I connect this task to this task. But what we want to do is really just describe the dependencies and develop the best task graphs based on these data dependencies alone. So this is Red Grapes here. This is an ongoing project. First prototypes are available, and it produces really a speed up to our large-scale HPC simulations already, and makes them much easier to read, because we're really describing the data dependencies between different parts of the codes inline, and now you can really understand how the code is structured and how parts of the code depend on each other. But we're not stopping there. If you really are running on a system, you will surely see that the way you communicate data, you want to reduce communication as much as possible, depends on the local structure of your system. So this becomes especially important if you have not just an HPC system at your hands, but also other parts of communication. For example, a strong data connection to your experiment, where the data from an experiment comes into the HPC system and you have to analyze it. And so this means that you really have to be able to describe the communication in a much more abstract way. And what we have been trying to do with Graybet is actually describe this via an interconnected graph and make the mapping to a certain system again open, so that if you now have a communication graph, you can actually online change that communication graph depending on the needs of throughput, bandwidth, and availability of resources. And we can even use different communication sockets below, so that we do not just rely on MPI, but can, for example, also use 0MQ or other libraries there. And we don't even stop there. We have to do optimum system usage. And this is Dodo, another project here where we see that really once you're on a heterogeneous system, you have to really describe how this system looks like to the code in order to really bring the information of what the code wants to do and what you have available as resources as close together as possible. This is partially done in big data analytics frameworks already. So this is great, but really doing this on the hardcore fundamental die level is really important if we go to petabytes per hour and higher rates, because then we cannot simply scale in the same sense anymore as we would do if we chunk just Twitter messages in any way, because data becomes interconnected and we have you do not have small bits of data that you can analyze independently. This is how you would usually scale on a standard homogeneous system, but everything is interconnected, and so you will always run into communication problems there. And again, what we do, if we know our hardware, we map all the resources that we have and that we need. So how much computation has to be done with what kind of data, all these resources can now be mapped onto our knowledge of the description of the hardware. And by this is very important. If you would usually do some active optimization of your code on a running system, this is itself is tricky, because usually the time to optimize, this is a global optimization problem usually, because you change something and then you see how the HPC system is reacting and if you're using it in a better way. So load balancing is a critical issue for complex simulations. But if you have a model of your system that you can store everywhere locally, you can actually understand how to use that system locally and to better optimize it. And you do not have to really wait for the answer of the system, but can have all the data available locally and create a good strategy to actually work with that. And finally, I.O. I told you I.O. isn't possible, but that's not really true. You can do I.O. But what is much more interesting is if you really couple different simulations together, or a simulation and a large-scale data analytics framework. So for example, we really have connected our large-scale HPC simulations that simulates these new particle accelerators for cancer therapy to really produce these scattering images. And these scattering simulations, again, are HPC simulations. So now we are having two HPC simulations running on the same system at the same time. And this simulation needs 10 billion, 100 billion particles from these simulations. The position of 100 billion particles and more need to be transferred to this simulation in a very short amount of time. And we're doing this with great help from the ADIOS team from Oak Ridge National Laboratory. We have set up an open self-describable data standard that is really keeping in track fair data principles, but also providing petabyte I/O at really high data rates of 100 gigabytes per second and higher on large-scale HPC systems and also for data analysis. So this standard is now being used in both data analysis for experiments and simulations. But if you look at it again, if you just go from disk I/O to in-memory, which is already a great thing, in-memory still means where the memory, still the question is, where is that memory? Is that in the host system? Is this the RAM of the CPU, or is this the GPU memory? And if you really go very close to where the data is produced, for example, inside the GPU that analyzes the data from the scattering experiment, or inside the GPU, for example, that does the simulation, then we have to think about intelligent modeling and analysis. So we really don't move the data anymore, and we do everything in the fastest part of the memory. And here I would have shown you a very nice movie. Unfortunately, for some reason, the forwarding of my screen this time didn't show up. So this is just the start. But what you would have seen is if you're now doing intelligent AI algorithms for the inversion of this scattering data, where I told you, you remember the dog and the cat, and where it became really critical because we are lacking information. And if you're putting in AI algorithms there, the standard algorithms fail to show you the ground truth data. And that's what you would have seen in the movie. If you go here to the AI assisted thing, you get exactly the ground truth in the same amount of steps. So these are much better algorithms now for inverting these non-convex problems. And this is really an important thing. And again, they're running, for example, on a GPU or an FPGA. So you can keep the data there. You just have to have a little different look at it and give it to that system right away. Same holds true for AI-driven surrogate models, where we basically take, for a very special system that we're looking at here, a very special one-electron Schrödinger equation in harmonic potential. We take that special system, take a general solver for this situation, but use it to actually create a solver that is AI-based. And here we have a mesh-free solver created using physics-informed neural networks that comes very close to what we see with a numerical solution. Actually, today I got better pictures for that I couldn't put in that anymore, that really show that there is total agreement now between those two. But the nice thing is this is now faster and it's mesh-free, so it's no longer resolution-bound, and it's depending on a certain mesh that you're using to solve this problem. So this is really a nice thing to look at. And it's smart. And finally, you really want to interact with all of this, because although we have all of this amazing AI, and maybe unsupervised learning will help us, or whatever, or quantum computing, there are still scientists who have to understand what's happening. And this is why we use interactivity. And you know this, that with Python, for example, we need really programming languages for this. So they need to be available on many systems and platforms. They need to produce performant code and high level of abstractions, but you just need to type in and it immediately changes something in your Jupyter notebook, for example. So you do the same thing with C++. We have teamed up with people from XUS and Xtensor and the Kling people who are doing an interactive C++ interpreter, and we have extended this to really be useful with Alpaca, and now providing you with full online Python JIT compilation using GPUs, FPGAs, and so on. So you have 100,000 lines of code that you compile, and then you take out a small part, you put it in your Jupyter notebook. It's pure C++. The data is on the GPU. You change something. The state of the whole memory is still persistent, and it works exactly like Python. You just click enter and the changes are immediately there. And if you want to see how this goes, there was a nice talk at GTC 2020 by Axel Hübel and Simeon Erik. So that was S21588. You can have a look at it. It's online available. So this is really a cool thing, even for those people who want to just use Python. Many of the things why Python is cool, and especially JIT compilation, are now available also with hardcore C++, ready for petabyte per hour I/O and so on. But we're not finished with that. As I said, better not move data at all. And so what you're seeing here is Isaac. That's our own tool for interactive visualization and really interacting with the data, which does take up a lot of the things that we thought about for Llama, where we basically said the data is already there. We just have to have a look at it in a different way. And that's exactly what Isaac is about. It does not move the data or change it in any way to be useful for visualization. It just has a different view of the live produced data on the GPU. It runs in parallel with the simulation on the same hardware platform and really has strong coupling to the data produced. So you're not moving data outside of the simulation at all. You're doing the visualization on the exact same data, on the exact same hardware as you're doing the simulation. And this is where you really get terabyte per second visualization capabilities now. You really can chunk billions of particles through, and it's in real time. So unfortunately, this would have been the killer movie at the usual end of the presentation. So, but since I'm running late, I'm not going to show you a lot of 3D cool stuff where you basically move around and see what's happening. But what is very important now is that we're combining this now with semi-supervised versions of our surrogate models, and that basically learn from these large-scale simulations. We will overlap experimental data with that, and thus provide you with a standard way of intuitively interacting with petabytes of data in a real-life manner, where you just can zoom in, look around, test your model, change your model online. You can do selections, and AI algorithms will help you, will learn from your selections, and will later find the same selections in similar simulations and in similar data sets, thus being able to do online reconstruction, online reduction of data really in a very concise and easy way, where you use your hands, your eyes, your keyboard, and nothing else, and it won't feel like it's a petabyte or even more. And this, I think, is really important, but this is just a part of where we are going. So the zoo of stuff that we need to have is just starting. And the way we are using these HPC systems right now with a scheduler and maybe as a single user on the whole machine, these days will be gone. This will be an online system available to many people at the same time. The resources have to really be scheduled. And if you're going back to that big science I told you about in the beginning, the HPC system will just be a tiny part of that, and it won't be the important part in the way of money. It won't cost as much as the experimental facility or the experimental time at that facility. But it will be a critical part of the operational stability, because without this system, you won't be able to understand your data in the time you're taking it, or even in the time that it is alive on the system. So without those tools, you won't be able to understand the data until it is deleted again. And this will be a very, very crucial thing to understand in the future. And this is where HPC leaves its standard realm of send out a simulation on a scheduler and wait for the result, and really become a discovery machine with which you interact. And it will actually be part of the overall facility that you are using. And this will become a very important new trend in HPC, I guess, because we will see the convergence of these two worlds, and we will see fruitful interaction between those two worlds. Large-scale data analysis of scientific data and HPC coming together in the future. And with this, I'm finished. I'm open for questions. I'm 1 minute late, but I didn't show you the video anyway, so that's fine. And I'm very happy again being here. And please fire at me with your questions. Thank you very much. So is anybody still here?
Yes,
see a lot of good, perfect. So I see a lot of people joining in. Thank you very much for being here. I'm very happy about this.
Michael, thank you very much. That's a lovely presentation. Excellent, very inspiring. Also, you know, some of us spend years, our entire sort of professional life in a single mode of provisioning of style of working, and this here is opening up new possibilities. So, are there any questions?
So my daughter just joined.
Oh, hello, hello.
We're all doing home office right now.
Hello, hello. So, do we have questions from the audience? I will ask questions in the meantime while we are waiting for others. How can this framework that you described, the discovery machine, be combined with this new trend that we are talking at the Euro HPC, which is federated HPC centers? That means then the boundaries between the particular machine are blurry. You don't need to know which machine you use. There will be lots of, like one might think of some sort of new HPC supersized cloud.
Yeah. So this is very critical. You have to still see that in the beginning, the data rates will be so high that you cannot move that data with current technology anywhere. You have to come as close to the experiment as possible in order to really reduce that data by 5 to 6 orders of magnitude before you can even think to bring it anywhere else. And this is due to the simple bandwidth problem and the bandwidth hierarchy that we are seeing right now. We would need even a terabyte per second interconnect between different sites would be laughable in that sense. So a lot of the data would first have to stay at the facility where this is taken. But if we can combine, or if we can, for example, provide planning of experiments in such a way that we have very intelligent algorithms that can do this reduction in an almost automated way in the beginning, then, of course, it is very interesting to not just have all the resources on site, because we usually, these facilities cater a huge amount of different even scientific fields, from bioscience to medical science and so on. And they are located everywhere in the world. So it would absolutely make sense, once you have reduced the data, it still be very complex and will still require a lot of later data analysis. But once you have reduced the data to an amount that is manageable, so maybe a petabyte or something, that you can transfer in a reasonable amount of time to somewhere else, then we're talking. And then this would be a true game changer, because it would actually help the facility to reduce their footprint in terms of HPC and free it again to a really daunting task of initial data reduction.
Thank you, Michael. Do we have questions? Panie Bartoszu, other questions from the audience? I can't see them here.
Yes, there are no questions at this time.
Okay. Then I completely cleared everything up. I'm always happy to do that.
Yeah. So, Michael, people find you. They have your email, or they know where you are. So hopefully there may be some further discussion ensuing. Just one thing that I haven't shown you on my slides. I've almost certain that we'll have another speaker from CASUS, from the part of environmental science. That would be Olaf Kolditz. Professor yes. Olaf Kolditz will be speaking sometime soon. I would like to let the audience know that we already have a schedule of talks up until mid-June.
Perfect.
So you please spread the word, announce it among your friends. There will be very, very interesting talks. As you've seen in my introduction, I will show again. Panie Bartoszu, perhaps we will show a few slides. Previous one, that's right. Next week we'll have Dr. Simon Mutch from the University of Melbourne, Australia. speaking about HPC simulations of the early universe. The week following that, we'll have Catherine Magouch talking about quantum annealers and computations using quantum annealers and how they differ from gated quantum computers and how to benchmark them and what sort of problems are sort of good for those systems, which are not. We'll have some talks following that from our own ICM. I will inform you that we are currently involved in several projects related to COVID-19, and we'll be reporting on the progress with those. And we'll have other talks on, we still have very interesting talks on quantum computers for all of those who are interested in that topic. Will be following after Catherine, and we already had Scott Aronson, as you know. So that will be continuing emphasis of the lectures. And with that, I thank you all for being here in a large number, and especially my friends. I can see Kim Leong from Singapore, and Clem Lau, and a few other old friends. So thank you for joining us, and I wish you all a very lovely evening or day or other part of the day, wherever you are. And for Polish listeners, I wish you very, very lovely long weekend, which starts tomorrow. Thank you.